This video is about relationships between two or more sets of data. In statistics, when we say that two sets of data are related, what we mean is that we know an algebraic function whose graph describes or explains the relationship between data in the two collections. For example, this table and graph show two collections of data where there doesn't appear to be any function that fits the pattern of data points in the graph. Or, here is a graph of data points where a straight line describes the relationship between the two collections. Or, there are other data sets where a straight line almost but not quite fits the pattern of data points. So, in these kinds of situations, we'll need to be able to measure the goodness of fit for various functions that come close to fitting the data. The functions don't necessarily need to have straight line graphs. For example, their graphs might form parabolas or other shapes. But, in any case, when a function does a good job of fitting data, we say that the data are strongly correlated. The topic we'll be investigating sometimes is called correlation and regression, and, just as in the case of centers, or points of best fit, there also may be several alternative ways that might be sensible to define what you mean by a line of best fit. For example, here is a graph showing 5 data points, which are labeled A, B, C, D, and E, and your task will be to move the points L1 and L2 so the green line minimizes the sum of the distances to the 5 points. In the first case, the line of best fit will be defined to minimize the sum of the simple straight line distances from the points to the line. In the second case, the line of best fit will be defined to minimize the sum of the squares of the distances from the points to the line. In the third case, the line of best fit will be defined to minimize the difference between sums above and below the line. In other words, this definition finds the sum of the red lines. Then, it finds the sum of the blue lines. And then, it minimizes the difference between these two sums. And, in the fourth case, the line of best fit will be defined to minimize the difference between sums of squares above and below the line. In other words, this definition finds the sum of the yellow squares. Then, it finds the sum of the orange squares. And then, it minimizes the difference between these two sums. What you will discover from these investigations is that, in general, these 4 lines are not the same. Furthermore, different definitions are based on different assumptions. And, these differences might lead to significantly different results. So, it is important to be aware of alternatives and the assumptions that they presuppose.